Okay, welcome to Chemistry A, Unit 4, Nomenclature and Formula Stoichiometry, Day 3 and Day 4. Let's get started. When we talk about how much stuff is involved in a compound or a molecule, we have to use a standard unit of measure, okay? And that standard unit of measure is called a mole. Now, we're not talking about the ground animal that burrows through your grandparents' yard that gets them so angry that Grandpa talks about it for 45 minutes at Thanksgiving dinner. And we're not talking about that ugly thing that somebody should go downtown and have a rat chew off of some people's faces. Not that kind of a mole. We are talking about a mole, and that stands for a grouping of a specified number of particles. The mole is the standard. Like we use in science, a standard unit of measure for distance is the meter. For volume, it's liters. Okay, that's the standard, and we base everything else off of standards. So, what does this basically mean? It means that there is a certain amount of a substance in every mole of an object or a compound. It does not matter what that is. Okay? A mole of a substance is 6.02 times 10 to the 23rd representative particles. And representative particles include molecules, atoms, and formula units. Okay? That's what they are. Alright? The number 6.02 times 10 to the 23rd is called Avogadro's number. And that number is named after the gentleman who figured out that there are 6.02 times 10 to the 23rd particles in any substance. Now what this means is 1 mole of gold equals 6.02 times 10 to the 23rd. That means there are 6.02 times 10 to the 23rd particles in 1 mole of gold. There's the same amount of particles in 1 mole of silver. There's the same amount of particles in 1 mole of hydrogen. There are the same amount of particles in 1 mole of helium. 1 mole of any substance will equal 6.02 times 10 to the 23rd power. You will need to memorize that number. Okay? Now, a representative particle refers to what is present in the substance. Like I wrote up there already, we're usually talking about atoms, molecules, or formula units. In this class, we will basically deal with just atoms and molecules. Okay? Now, a mole of any substance contains Avogadro's number of representative particles, 6.02 times 10 to the 23rd particles. So, if I have a question that says, look, I have X amount of particles, how many moles do we have in that system? This is just a conversion process. It's no different than going from, I have 10 meters, how many centimeters? How many millimeters? Okay? And this is what we're going to talk about right now. It's converting particles to moles. To find the moles when given representative particles, use the following conversion factor. Representative particles times 1 mole over 6.02 times 10 to the 23rd will equal blank moles. So, you're looking at your example or your problem, and it says, find the number of moles in 12.5 times 10 to the 23rd power of whatever atom we're talking about. You would use this. You would use this formula. Okay, so let's take a look at how we can convert the number of atoms to moles mathematically. We are on page 291, and we're going to look at sample problem 10.2. I ask that you get your book out and please follow along. Magnesium is a light metal used to manufacture of aircraft, automobile wheels, tools, and garden furniture. How many moles of magnesium is 1.25 times 10 to the 23rd atoms of magnesium? Okay, the first step is to always list what we know. Okay? We know the number of atoms of magnesium. Okay, and that number is 1.25 times 10 to the 23rd atoms of magnesium. Okay? We know that 1 mole is equal to 6.02 times 10 to the 23rd. Okay? What we don't know, the unknown, is the number of moles. So therefore, we need to use the conversion factor of 1 mole over 6.02 times 10 to the 23rd power. That is our conversion factor. So we take what we have in the problem and multiply it by 1 over 6.02 times 10 to the 23rd. And in this case, it's 1.25 times 10 to the 23rd. Now, anytime you multiply a number by 1 over another number, like we have right here, it really becomes 1.25 times 10 to the 23rd divided by that number. So it becomes 1.25 times 10 to the 23rd over 6.02 times 10 to the 23rd, which is a division problem. And when you divide that out, you get 2.08 times 10 to the negative 1 mole. So that's how many moles we have in 1.25 times 10 to the 23rd particles of magnesium. Okay, so what happens if now I tell you the number of moles that we have and I want to know how many particles or atoms or molecules we have? Well, in the last problem we divided, and what is the opposite order of operation for division? Of course, it's multiplication. So when we're trying to find the particles given when moles are given to you and you're trying to find the amount of particles, use the following conversion factor. Moles multiplied by 6.02 times 10 to the 23rd over 1 will equal the number of particles. So this number right here, this information is in the problem already. In the problem. Okay? This conversion factor is something that you're going to have to memorize. This is what we're calculating for. So let's take a look at page 292, sample problem 10.3. I'll give you a second to get there. Okay, propane is a gas used for cooking and heating. How many atoms are in 2.12 moles of propane? C3H8. All right? So, what do we know? We know that there are 2.12 moles of propane. And we know that 1 mole of propane is equal to 6.02 times 10 to the 23rd. What we don't know is the amount of particles. So we have to calculate that. And to calculate that, we use the conversion factor listed above. So 2.12 times 6.02 times 10 to the 23rd over 1 mole of propane. And when we do that, that will equal the amount of propane for 1 atom. What's the catch here? Propane has C is C3H8. This conversion factor is for 1 atom. How many atoms do we have in propane? We have 11. So what we have to do here is add a step. and we have to multiply by the number of atoms. So it becomes 2.12 times 6.02 times 10 to the 23rd times the number of atoms. And when we do this, we then come up with 1.40 times 10 to the 25 atoms. Okay? That is our answer. 1.40 times 10 to the 25 atoms in 2.12 moles of propane. Okay, so now we're going to talk about the atomic mass of an element. And that atomic mass of an element is expressed in grams, is the mass of the mole of the element. The mass of a mole of an element is its molar mass. For example, carbon. Carbon has a molar mass of 12 grams. Hydrogen has a molar mass of 1 gram. Where do I get this information from? Correct. The periodic table. Okay? When you look at the periodic table, you will look up the fact that carbon has an atomic mass of about 12. We round that off and just use the number that is the closest to it. Okay? So carbon's molar mass is 12 grams. Hydrogen's molar mass is 1 gram. If you look at the periodic table and you look up any element, you can determine what that is. So I'm going to look it up right now, and I'm going to look up oxygen. Oxygen's atomic mass is approximately 16. Okay? And that is given to you in the periodic table under atomic mass. All right? So the mass of a mole of a compound. All right? The mass of a mole of a compound. To calculate the molar mass of a compound, find the number of grams of each element in 1 mole of the compound, then add the masses. So let's take a look at page 296, sample problem 10.4. Finding the molar mass of a compound. The decomposition, which means breaking down, of hydrogen peroxide, H2O2, provides sufficient energy to launch a rocket. What is the molar mass of hydrogen peroxide? Okay, so list what we know. Well, we know the formula is H2O2. All right, we know that 1 molar mass of hydrogen is 1 gram. And we know that 1 molar mass of oxygen is 16 grams. I looked that up on the periodic table. All right? So what we don't know is what is the total molar mass of that compound. That's what it's asking. What is the molar mass of that compound? Okay? Well, here's all you do. This is very simple. You take each compound and multiply them by the molar mass of 1 atom multiplied by the multiplied by the number of atoms. So in H2O2, we have H equals 1 gram multiplied by 2 atoms. So it is 2. Oxygen, we have 16 grams times 2 atoms. So 16 times 2 is 32. You add those up, and we get 34 grams. So, the molar mass of a molecule of H2O2 is 34 grams. Okay? Our next part of this lecture is going to be in another video. That will be in Day 3 and Day 4 notes, video part 2. So we'll look forward to seeing you then.